the motion from images and the inertial measurement. Daniels and I went to college and went to grad school together in Carnegie Mellon in 1998. We've been good friends since. We've been drinking together and taking the same classes. And Daniels graduated, I think, last year from CMU and was working at Honeywell for a year. Now he's here for a candidate for the research scientist.
I don't usually talk into the microphone, so if you catch me lowering it or not repeating a question, just let me know. Okay, good to go. Okay, so the title of my talk is Motion from Image and Inertial Measurements. Can you hear me okay? A little louder? Okay. So let me start off right away saying these materials are on the web. The slides, my thesis and things like that are up there. Okay, so it's pretty well known that for an image sequence, we can recover the 6-degree freedom camera motion without any knowledge of the camera surroundings or a priori knowledge, and without an external reference like GPS. This is a good example. So this is a sequence taken from a turntable by Andrew Fitzgibbon, and what you're seeing across the top are 6 frames from this maybe 50-frame sequence, and on the bottom you're seeing the results of that. So each of those little frames you see in the circle on the bottom are the 6-degree freedom or 3-dimensional rotation and 3-dimensional translation of the camera at the time of each image. And then in the middle, you see that from the camera positions, he's reconstructed a little, what we call a sparse model of the dinosaur. Okay, so there are a lot of applications for this type of thing. So modeling from video is one. This is an example from an old collaborator of ours named Yuji Uchida. Across the top, you see 3 frames from a short sequence of the Grand Canyon. And what he's done is he's used the factorization method, which I'll talk about a little bit, to get the position of the camera at each time. And then once you know the position of the camera at each time, you can do like a multi-baseline stereopsis to figure out kind of the dense structure of the scene that you saw. And that's what you see on the left. And then on the right, he's just taken that structure and texture mapped it. Oh, some reverb or something? Okay. I'll speak right into it. Okay. Okay, so another possible application that we're interested in is micro-air vehicles. So these things are really coming on the scene now. They're little things that can fly, say, in cities or in other restricted areas for surveillance. A good example is AeroVironment's Black Widow. It's a little 6-inch aircraft that can fly for about an hour on its battery, and it carries a little camera that's just a few grams. So if you could estimate the motion of this thing using the camera, you wouldn't, say, have to carry a GPS receiver, or you could go under the canopy in the forest or something where GPS wasn't available. Okay, rover navigation's another good one. You know, there's no GPS or other external positioning on Mars. So for example, the Hyperion rover that CMU built is a kind of prototype intended to test Mars rover navigation. So we put our camera on Hyperion and used the camera to try to estimate its 6-DoF motion, and I'll talk a little bit more about that. A more terrestrial application for ground vehicles is David Nister's system, and I believe that's his equipment on the Perceptor program vehicle from CMU. Okay, search and rescue robots is another good example. These things Okay, so this guy's called Rex. He's being developed by several universities jointly, and he's a very simple kind of cockroach-like design. He's got 6 actuators or legs that kind of move independently and without a lot of intelligence, but that lets him get over rough terrain. In particular, they're thinking that if they could send him into rubble at an accident scene, maybe he could find survivors, but of course there's no GPS in rubble. So if you could estimate its motion from the images that the cockroach sees, that would be helpful for locating the survivor's position. And then another thing, just one last example, NASA's been working on this thing they call, NASA Ames has been working on this thing they call the Personal Satellite Assistant. It's a little kind of disembodied head that flies around the station using fans. And they don't want to put up fiducials or other external references on the space station because space is constricted. But it's got 4 stereo cameras, 4 stereo pairs on it. So if you could estimate the motion of this thing in 6-DoF, 3-dimensional rotation and translation using the cameras, you'd be in a good shape. All right, so for all these problems, there are a few things in common. We want 6-degree freedom motion, meaning the 3D rotation and translation. We don't want to have to instrument the environment, and we don't want to have to require GPS or some more archaic absolute positioning system. In addition, for things like MAV or robots looking for survivors, we want small, light, and cheap sensors and disposable sensors. And really, the thrust of this talk is that we want to do this over the long term. And by long term, I really mean two things. One is the obvious thing, that the absolute time or distance is long. The other thing, though, in the context of vision, is that only a small fraction of the scene is visible at any one time. And I'll show you some examples of that. All right, so given all these requirements, cameras are promising sensors. And a lot of algorithms for estimating the motion of the camera already exist. But at the same time, where are the kind of easily run or consumer-type systems for estimating the motion of all of these applications? And for doing things that people want to do, like automatically modeling rooms, buildings, or cities from a handheld camera. Okay, so my answer to that is that motion suffers from some long-standing difficulties. And really this work, what it does is it says, we've been trying to do this for so long, can we step back and try to objectively examine the reasons why we still can't do this after all these years? And so the four thrusts here are trying to add cheap, what I call epsilon inertial sensors to the problem, which are kind of the least, or the cheapest, least accurate inertial sensors that we could add to kind of regularize the problem. Robust image feature tracking, and I'll talk a little bit about that. Recognizing previously mapped locations so that we can limit drift over the long term when we revisit a site. And then exploiting omnidirectional images. I have some slides at the end. I won't talk about this unless people are really interested, but I can point you to the website also. All right, so this is my outline. I'm going to start by giving you a little bit of a refresher and technical introduction to motion from images. Then I'll build on that with my algorithms for motion from image and inertial measurements. We'll talk a little bit about robust image feature tracking, this idea of using reacquisition or recognizing a previously mapped scene to do long-term motion estimation, and then I'll just conclude very briefly. All right, so when you're trying to estimate the motion of a camera or a vehicle to which a camera is attached from images, a kind of two-step process is common. So the first is sparse feature tracking, and the second step then is estimation. For sparse feature tracking, the inputs are the raw images, and the outputs are the projections or the tracking data of sparse points in that sequence. Okay, so this is a kind of a classic example. It's the hotel sequence taken by, I believe, Carlo Tomasi at CMU. It's about 20, the subsequence I've taken is about 20 images. We've automatically extracted about 100 points that are in well-textured parts of the image, and we've tracked them using Lucas Kanade through that 20-image sequence. Okay, now there are kind of, I think, two paradigms for doing this type of image feature tracking. The first is template matching, which is a kind of venerable method, and basically you've got some point in the first image, you want to know where that point is in the second image. So you just extract a little, say, 11 by 11 or 13 by 13 mask of intensities around the first point, and then you do maybe a raster search in the second image to find out what location maximizes the correlation between that mask and the mask around the kind of candidate point in the second image. Okay, now Lucas Kanade, also at this point a pretty old method, is just a way to do that a little more efficiently. So basically it says we've got some error that's similar to the correlation error, the sum of squared distances, and instead of doing a raw raster search, we'll just do a nonlinear minimization to minimize that error. And I'll talk a little bit more about that. And then there's the second paradigm, or at least in my kind of mental hierarchy, which is independent extraction and matching. So instead of extracting features in one image and then trying to find them anywhere they might be in the second image, we'll just extract salient points in both images and then try some combinatorial optimization to match those two sets of points. A lot of people these days for efficiency are using Harris features. They're kind of similar to the features I showed you in the hotel example, but they're efficiently extractable. And then something that's a little less efficient but more accurate is scale invariant feature transform key points by David Lowe. And I've used this in some of the work I'm going to show you here. Okay, so the second step in that motion from images paradigm is the estimation part. So the input, of course, is the output from the tracking phase, which are these projections or tracking data. And the outputs are the 6-degree freedom camera position at the time of each image and the 3-dimensional position of each track point. Okay, so if you do bundle adjustment, which I'll talk about in a little bit, for that hotel sequence, this is what you get. What you're seeing on the left, or I should say what you're seeing altogether, is a kind of a top-down view of the reconstructed 3D points on the left and the 6-degree of freedom camera positions on the right, viewed from above. So for example, this area here is the front of the hotel. This is one of the roof lines, and the other part there is the other roof line. The center of the axis over there is the position of the camera's center, or say lens position at the time of each image. And the motion that bundle adjustment recovered there is at least roughly the correct motion. All right, so the methods for doing the second step, the estimation step, a lot of them are pretty well known. Bundle adjustment's kind of the go-to method when you have the time and computational resources. And I'll talk about that in a little bit of detail. Basically, you're just using nonlinear minimization to find camera positions and point positions that are consistent with the projection data that you extracted. And a key part about bundle adjustment is that it's a batch method, meaning that you assume that you have all the data at once. So if you have a 100-image sequence, you're going to assume that someone handed you all 100 images before you start. Kalman filtering, at least in this context, is similar to bundle adjustment. It's just a way to minimize the bundle adjustment error iteratively, meaning that someone hands you 10 images to initialize. You do that with bundle adjustment. And then on images 11, 12, 13, 14, you produce an intermediate result for that image from the new data. Okay, the variable state dimension filter is becoming more common now. It's a combination of these two ideas. Instead of just finding a camera position for the current image, you'll have a sliding window. So if you initialize with 10 images, you'll do bundle adjustment on images 1 through 10. And then when you get image 11, instead of just finding the position for image 11, you'll have a sliding window. So you'll refine your positions for 2 through 10, and you'll find a position for 11. And then there are some methods that I think of as ad hoc. Some people would argue not, but they're what I call the 2 and 3 frame methods. So instead of trying to minimize any error, just say apply bundle adjustment or epipolar geometry estimation to 2 or 3 frames at a time, and then just concatenate those coordinate systems that you found. So I say that it's ad hoc in the sense that you can't point to some image in the air that you're minimizing with respect to. Am I okay? Can you hear me in the back? Okay. All right, so let me talk a little bit about bundle adjustment, because some of my work on image and inertial measurements is built on top of it. So from the tracking data, again, this is the hotel sequence. What we have are kind of a 2D matrix of measurements. There are the positions of each point J that we tracked in each of the images I. And suppose that from some magic source, we also have estimates of the unknowns we want to estimate. So for example, the camera rotation and translation at the time of each image, and the 3-dimensional position of each point that we tracked. Given those estimates, we can compute the reprojections. So that's just taking the estimate of the 3-dimensional point and converting it into the camera coordinate system at the time of the current image, using the estimate of the rotation and the estimate of the translation. And then once you have the estimate of the point in the camera coordinate system, you can just compute a reprojection of that 3-dimensional camera coordinate system point into the current image. And now this projection operator, I've written it pi. Typically this would be perspective projection for a conventional camera, but some of our work's been on omnidirectional cameras, which combine a conventional camera with a mirror that expands the camera's field of view. So in that case, this would be something more complex, but still tractable. Okay, so once you've done that, you have the observations, which are in red, and you have these reprojections, which are in blue. And basically what you want to do is find estimates of the camera positions and point positions that minimize this error, or some error like it. Okay, so what bundle adjustment minimizes is the square error between the reprojections, pi, etc., and the observation xij, with respect to everything we're trying to recover, those camera positions and 3D point positions. Okay, if you do that for the hotel, you get this result that I showed you. And the problem is that, even for bundle adjustment, which is this batch kind of heavy hammer method, the estimation step can be very sensitive to incorrect or insufficient feature tracking, camera modeling and calibration errors. So for example, if you don't know the camera's focal length properly, or if it's got some poorly modeled radial distortion, it can be very sensitive to outlier thresholds. And sequences with degenerate camera motions are still problematic for this method. Okay, in addition, an iterative batch method like bundle adjustment can still have poor convergence or fail to converge if observations are missing. which is a case we're really interested in. You know, for example, if at any one time in any one image we're only seeing 10% of the scene or 1% of the scene, and we don't have a good initial estimate of what the full motion was, that's a problem. Or if the initial estimate's poor. Okay, now recursive methods like the IEKF or the the Kalman filter or the VSDF also suffer from some problems. So, for example, they tend to have prior assumptions on the motion. So you may have some prior expectation of how fast the camera is moving or how fast it's accelerating. And in addition, you know, with these recursive methods, basically what you're doing is you're doing a minimization over the current frame or over the current window of frames with a prior that results from, you know, all the data that went before. And you're incorporating all the data that went before into some distribution on the camera positions and point positions. And for instance, in the Kalman filter and VSDF, that distribution's modeled as a Gaussian, which is grossly wrong in a lot of cases. Okay, and I think of the resulting errors in two ways, at least for long sequences. So there are gross local errors. You know, if you have gross mistracking and you don't catch it, you know, your camera motion may have been something tame like this, and you estimate it to be, you know, from here to Santa Monica. That's a gross error. Or, you know, you estimate a point that you saw in front of the camera to be somewhere behind the camera. That's a gross error, and for a long sequence, it kind of shuts you down, right? Because you're doing basically odometry, and once you get a gross error in your odometry, you're done for the day. Okay, and then the other thing is long-term drift. So even if you work hard and you do a robust estimation to eliminate all of the gross local errors, like I said, you're doing odometry, so you're probably going to accumulate some long-term drift. Okay, so this is just a nice example of some of these difficulties. This is an arm in one of the robot labs at CMU, and we've attached a camera to the end of the arm, and we put it through this motion. If you'd look at this motion from above the robot's workspace, you'd see kind of that it traces out a cloverleaf pattern in X and Y. And then it kind of alternates up and down in Z. Okay, so this is the sequence that the camera sees. It's 151 images. I've tracked 23 points on it by picking out some points by hand, running Lucas Kanade on it, and then manually correcting the results of that tracking. And if you then put that tracking data into Lucas Kanade with a reasonable estimate, you get this kind of horrendous estimate that's the crooked black line. And what you're seeing here is the XY view of the robot's workspace. So you see this cloverleaf pattern that's basically the correct motion, which is that smooth dashed dotted line. The 7 boxes there are the control points for the motion. So we told the robot to go through those 7 points and basically execute a circular arc between them. And then, like I said, that black erratic line is the, quote, optimal estimate from images only, which is the bundle adjustment estimate. And what's happening there is that because there are so few points, because you see so few of the points in every image, it's just very sensitive to the small 1 and 2 pixel errors in that tracking data, and it's sensitive to the small errors in the camera calibration, meaning the focal length, radial distortion, and things like that. Okay, so that's just a brief kind of crash course in motion estimation from images and the kind of lingering problems with it. One way that we've tried to address those problems is to incorporate, like I said, the epsilon or least possible or least useful inertial measurements into it, and I'll talk a little bit about that. Okay, so it's possible to just take inertial sensors like a gyro and an accelerometer and integrate those over time. So if you integrate gyros, which give you angular velocities over time, you'll get rotations. And if you integrate accelerometers, which give you acceleration over time, you integrate it twice, you'll get positions. So if you do that, and if your model of the inertial sensors is good enough, and if the inertial sensors themselves are good enough, you can do quite well. So I've been told, you know, I've never actually seen it, that submarines carry inertial sensors that are gimbaled, and they're about the size of a side-by-side refrigerator. And using those inertial sensors and 50 years of experience in inertial sensor modeling, they're able to go from one side of the planet to the other underwater without coming up for GPS correction. Okay, but in a lot of our applications like the MAV, obviously our 6-inch vehicle isn't going to carry a sensor the size of a side-by-side refrigerator. Instead, what we have are maybe sensors that are about 1 inch wide. So this thing on the left is our rate gyro. And in our experiments, we've used 3 of these. They're single-axis gyros. The thing on the right is a cheap accelerometer intended for airbag deployment applications in cars, and that's also about an inch cubed. That's a 3-axis accelerometer. And if you just take these and try to integrate their results, once for the gyro, twice for the accelerometer, you'll run into a lot of problems. One reason is noise. They're noisy sensors and they're cheap, and every reading you get has some independent Gaussian noise that will integrate over time. And then there are unmodeled nonlinearities. So, for example, you would typically assume that the angular rates reported by a gyro are some linear function of the voltage that it outputs, which isn't really true. Okay, and then kind of an even harder problem is that, at least with the accelerometer, its output depends on all sorts of things, like its orientation relative to gravity, the actual acceleration you're trying to uncover, the slowly changing bias in the accelerometer, and so on. And unless you have some independent way of estimating all these unknowns, you can't even really start. Okay, fortunately, image and inertial measurements are highly complementary. With inertial measurements, we can decrease the sensitivity that I talked about in the image-only estimates to bad tracking or bad calibration. You can establish 2 of the rotation angles without drift because the output of the accelerometer does depend on gravity. And you can establish the global scale. So I haven't really talked about this, but if you just move one camera through the environment, you can recover the 3-dimensional structure of the environment and the motion of the camera, but you can only do so up to some global scale. And the analogy that I like to use is 2 eyes looking at a tree, right? So if you know that your 2 eyes are horizontally displaced and you see 2 images of a tree, you can figure out kind of what the shape of that tree was. But unless you know the distance between the eyes, you don't know if your eyes were 6 inches apart and you're looking at a model of a tree, or your eyes were 3 meters apart and you're looking at an actual tree. Okay. So on the other hand, going on with this complementary discussion, with the image measurements, we hope to reduce the drift in integrating these inertial measurements. So for example, if we happen to see the same thing for quite a long time, or if we come back to a thing that we've seen before, that will work. And also it gives us a way to bootstrap this process of estimating all the unknowns that the accelerometer measurements depend on. Okay, so my work on image and inertial measurements has developed batch and recursive algorithms for doing this. And I'll give you a little feel for both of those. First, let me talk about my simple model of the inertial sensors. So with the accelerometers, they're relatively simple. We'll assume that the angular velocity that we see is the actual angular velocity, modified by some slowly changing bias and some kind of per measurement independent Gaussian noise. The accelerometer measurements are hairier, like I said. They're the actual acceleration we want, modified by gravity, rotated into the sensor coordinate system, and then, like the gyro, modified by a slowly changing bias and an independent Gaussian noise. Okay, so with that model of the sensors in hand, we can try to do a minimization analogous to bundle adjustment. And this is the error term that I'm looking at. It's an error that combines image and inertial error terms. And the image term is just the bundle adjustment error that we saw before. The inertial error term is a little more complicated, and it's 3 terms: rotation, velocity, and translation. And as an example of how this error term works, let me show you the translation term. And I'll start with one of the terms in that sum. Okay, and this is what that looks like. So we're thinking about the time between 2 image readings, tau I minus 1 and tau I. And we've got some estimate that we're iteratively improving of the camera position at time I. So, or the camera translation in this case at time I. So what we do is we take all the inertial measurements between those 2 times, and we integrate them forward from that first estimate of the translation until the second time. And then what we do is we also have some estimate of the translation at that second time that we're iteratively improving. So the error we want to minimize is the difference between our estimate at that time and the result of integrating from the previous time. In our prototype system, we took images at kind of the standard frame rate, which is about 30 frames per second. And we took inertial readings at the highest rate that our little acquisition board would give us, which was about 200 hertz. So between 2 images, we're typically integrating over, say, 6 or 7 inertial readings. Okay, so that was one term of the translation error. And if you look at the whole sum, basically what you get is a chain of these errors. And you just try to minimize all of those errors jointly. And if we didn't have any, say, image measurements to kind of get this process under control, obviously the solution that would drive all those errors to zero would just be the solution that integrates the inertial measurements. Okay, so that was the translation error. The rotation error and the velocity error are similar, but they're simpler because they don't depend on as many unknowns. Now that translation error is the one that depends on the most unknowns. It depends on the 2 times, which we assume that we'll know. All the inertial measurements between those times, which again we'll assume we know. The camera rotation and translation at the time of the previous image, which are unknowns that we also estimate in a raw bundle adjustment. And then the gravity direction, the gyro and accelerometer biases, and then something we don't estimate in a bundle adjustment, which are the linear velocities of the camera, which we need to integrate the accelerometer. Okay, and if we do that for that robot arm example that I showed you, we get this, which is the same chart that I showed you before. There I described this cloverleaf estimate as kind of the correct estimate, and in fact that's actually the estimate from this image and inertial minimization or bundle adjustment. Okay, now we're interested in doing this live on robots, so we also built a recursive Kalman filter or iterated extended Kalman filter to do this. And I'll just briefly talk about it. So the dashed dotted line here again is the same batch or bundle adjustment estimate that I showed you before. And then that solid line is, for this example, the best Kalman filter result that I could achieve by kind of tweaking the parameters of my filter. Okay, but I did encounter a lot of problems with the IEKF for this application. These assumptions that I mentioned at the beginning of the talk, the IEKF does require that you have some estimate of how fast you expect the camera to be moving or accelerating. And if that expectation is wrong, then you're kind of done for the day. It doesn't model the relative error between adjacent camera positions, which you kind of want to know because we're using relative camera positions to triangulate the position of points. And the reason for that is that it only has one camera position in the current state. So, kind of based on these statements, I think a nice approach for the future might be to take that batch algorithm and convert it into a sliding batch algorithm using the VSDF. And that would fix up probably both of these problems. Okay, and one example of kind of failed IEKF result is shown on the right. This figure on the left is the one that I showed you. It's the best IEKF result that I could generate from this data. And the one on the right is generated, that horrific solid line there is just generated by picking the propagation variances, our expectation of the camera's changing accelerations incorrectly. Okay, so just to recap that work on image and inertial measurements, our sensors are images, gyro, and accelerometer. We did a batch algorithm which uses all the measurements at once and a recursive algorithm, which is more efficient. And my thesis actually includes a very large suite of experiments trying to evaluate these methods and trying to establish some basic facts about motion from image and inertial measurements. So for example, given just image, gyro, and accelerometer, can we reliably estimate the gravity direction, and can we reliably estimate the scale? And for instance, one thing I found is that even with my, this may be on the next slide. No. Okay, one thing I found is that even with my cheap inertial sensors, my $200 accelerometer, we could estimate the global scale to about 5%. All right, so image and inertial measurements is good, but one thing I did find was that adding these epsilon inertial sensors didn't really improve the system's robustness to mistracking. So even minor mistracking, even though we had inertial sensors, could still produce a pretty bad motion estimate. So I revisited the feature tracking problem. And the other issue is that even though inertial sensors do help the robustness of the situation, of course, the vast majority of sequences that you're just handed or that you may find on the web, don't have inertial measurements. Okay, so we tried to look at better tracking specifically for 6-degree freedom camera motion estimation. And the remaining results in the talk will be image only. So kind of put up a Berlin Wall in your mind between the inertial stuff that went before and the following. Okay, so Lucas Kanade, which I talked a little bit about before, has kind of long been the go-to feature tracker for these types of applications. For example, this is one of the baseline methods implemented in Intel's Open Computer Vision library. And the idea, just to review, is that it minimizes an error like correlation using general minimization. So it's using a second order Gauss-Newton minimization. And it evaluates the matching error at only a few locations. So raw correlation matching, if you have a 640 by 480 image, would be looking at 640 times 480 locations. Typically, Lucas Kanade, if you have some reasonable initial estimate of where the point is in the second image, may only need 5 or 6 evaluations. And one thing that a certain charm of Lucas Kanade is that it can find your positions to subpixel resolution. And what I call the Folk accuracy of Lucas Kanade, or the number that people kind of cite without any evidence, is about 1/10 of a pixel. Okay, so like I said, Lucas Kanade is this nonlinear minimization applied to basically correlation tracking, but just that isn't enough to generate a tracker, right? So you need to add in some other glue to make that work. You need to know which features you're going to track. You need to identify mistracked features, or features that become occluded because of three-dimensional structure, or features that leave the image. And you need some way to handle large motions. So, Lucas Kanade is a nonlinear minimization, which means that you need some initial estimate of where that thing is. If the image motion is 100 pixels, well, it's not good enough to just say, start where you were in the previous image. You need some initial estimate of that 100 pixel motion. And the heuristics on the right are the ones that are usually used with Lucas Kanade. Basically, the tracker that I'm going to show you analyzes Lucas Kanade. It says all 3 of those heuristics are wrong in certain important scenarios. So we're going to try to build a tracker specifically for 6-DoF motion that fixes up those problems. Okay, so this is the same sequence that I showed you before. Like I said, this was a bunch of points picked out by hand, tracked with Lucas Kanade, and then there was a pretty excruciating manual correction to get the correct position of those 23 points over 150 frames. And the reason is that if you look at the sequence, there's a lot of poor texture. I mean, there's some texture on the ceiling tiles that you're seeing. But there's also a lot of one-dimensional texture that isn't friendly to Lucas Kanade. In the bottom right-hand corner, you see the grate on a light. There's a lot of repetitive texture. So, every XY position on that grate looks the same to Lucas Kanade. And then, if you remember the sequence, it kind of rotates pretty wildly. So it goes through about 270 degrees in 150 frames. And that kind of rotational motion is not very friendly to the model that Lucas Kanade uses. Okay, so smalls, I call the new tracker smalls. It's targeted specifically at 6-DoF estimation, meaning that it exploits the rigid scene assumption. You're moving your camera through rubble, or what the military people call the urban canyon, something that's basically a non-moving environment. It eliminates those 3 heuristics that I described that you normally use with Lucas Kanade. And then it uses, like I mentioned at the very beginning of the talk, it uses this scale invariant feature transform that David Lowe developed. Okay, so it's 4 steps, and I'll try to be brief here. The first step is estimating the epipolar geometry of every pair of images. So we'll use SIFT to establish matches between 2 images, tentative matches. We'll estimate using just a 2-frame bundle adjustment the relative motion, meaning rotation and translation, between those 2 images. And then we'll get the epipolar geometry relating those 2 images. And what I mean by that, I'll kind of say quickly here. So these are the SIFT matches between 2 images taken from Hyperion in the Atacama Desert in Chile. And what you're seeing on the top and bottom are the 2 images with the line showing the correspondences that SIFT found between those 2 images. And these 2 images are pretty highly textured, and the motion's not extreme. So out of those, I think 100 matches, 100% of them were correct, which is good, but actually not atypical of SIFT. Okay, and then this epipolar geometry that I mentioned, basically you've got some points in the first image, and you want to know where they were in the right-hand image, and you know the geometry or the motion between those 2 camera times. So what that tells you is, for every point in the left-hand image, just back project that ray from 2D into 3D. And since you don't know how far away the thing is a priori, that gives you a ray out into the scene. But you know how the camera moved, so you can reproject that ray into the second image, and that's what these lines are for these 5 points. And so you know where the point is somewhere on that line, but you don't know where on that line it is because you don't know the depth. Okay, so the second step then is to track along the epipolar lines to determine the depth. And you want some initial estimate, so I use the the position of the nearest SIFT translation is the nearest estimate. And then just do a kind of basically correlation search along that line. And then refine that position, that discrete position with Lucas Kanade, which will give you the, say, 1/10 pixel accuracy. Okay, the third step is prune away features. So I prune exclusively based on the geometric consistency of the features between those two times. So it's pretty straightforward. Okay, and then extract new features. So typically what trackers do is they try to extract new features in textured areas on the assumption that those are the features you're going to be able to track. Now what we found when we we constrain the tracking just to the epipolar lines is that we can track almost anything. You know, even a very weakly textured point, or say a point that may be on a line perpendicular to the epipolar line, we can really track without too much difficulty. So we get rid of the heuristic that demands texture. We replace it one that says, give us as much coverage as you can in the image. And the rationale there is that shape for motion or 6-degree freedom camera position is generally easier if you have a wide field of view camera. So if you're letting your features all clump up in one part of the image, you're kind of throwing away, say, 50 degrees of your field of view, which you don't want to do. So try to get coverage everywhere in the image. Just say get the full 70-degree field of view of your camera. Okay, so that was, I know that was very brief, but here's an example of what it does. And this is a sequence that we took by putting a camera on the back of the Hyperion rover when we were in Chile. And the camera in this case kind of points off 45 degrees towards the horizon on the back of the rover. And what this does is it's intended to give us a view of the horizon so that we can see receding points for a long time, but also see some points that are moving quickly off to the left so that we can get some good parallax. And this is the result of the smallest tracker on the sequence. Now I know it's kind of fast. One heuristic when you're looking at tracking data and image sequences is to kind of blur your eyes a little bit. And actually your visual system's pretty good at seeing, you know, it's a little bit jarred by inconsistent tracking. And in this case, the tracking's almost 100% accurate. And, you know, almost to the point that the points look like they're part of the scene. All the stuff that you're seeing around the border, this stuff is like a haze filter that we put on the camera. It restricts the camera's field of view a little bit. The thing you're seeing at the very top is Hyperion's solar panel, and then this thing at the bottom that kind of comes and goes is the shadow, Hyperion shadow. So, you know, the idea of SMALS was that we're going to use its output as the input to our 6-DoF motion estimation. And these are the results of that motion estimation shown from above. So the graph on the left is the ground truth odometry from Hyperion. And one reason we're doing 6-DoF motion estimation is that odometry does drift over time. But over the scale of this example, and given Hyperion's kind of magically good odometry, we found that actually that estimate on the left is almost exactly the correct motion. Now, the estimate on the right is the estimate that we get by using the SMALS output fed into a Kalman filter. And it doesn't have any gross local errors, but it does drift over time, and I'll come back to that. Okay, so just to recap, SMALS is just a revisitation of this long time tracking problem. It exploits the rigid scene assumption, meaning that we intend it specifically for 6-DoF motion. And it eliminates the heuristics that kind of limit Lucas Kanade's application to a lot of real sequences. It allows hands-free tracking for real sequences. So for example, at Honeywell, you know, if we're writing a proposal or something, someone can just hand me a sequence from Honeywell's, you know, new vehicle. And a lot of times it just generates the right tracking without any tweaking or any manual correction from me. But it can still be defeated by textureless areas or repetitive textures like this ceiling grate. And I'll show you some examples of that. Okay, so let me talk briefly about this problem of long-term motion estimation, which is really what all this builds up to. You know, the image and inertial integration and the SMALS feature tracker are kind of designed to remove these gross local errors. Once you've eliminated gross local errors, how do you move on and how do you really try to estimate your motion over some indefinite time with some accuracy? Okay, I think this is clear. if you don't see the same thing in the images all the time, you're kind of reduced to odometry because you're not estimating the camera's position with respect to one set of points. This is the example again from the Atacama. It's a great example. For instance, if you look at the very top in the blue there, you'll see where on 2 of the loops the rover came back to exactly the same position. And when we look in the image sequence, we can see that in fact the images at those 2 times are almost exactly the same image. So it seems that that's exactly correct. The estimate by piping smalls into the Kalman filter is the thing on the right. And for instance, you'll see there at that position they don't actually come together. There's like a 2 or 3 meter error there. Okay, so to limit drift, we need to do 2 things. We have images, so we need to look in the images to see when we've come back to a place where we've been before. And we need to exploit that in the second step, which is the estimation step. And I built a kind of proof of concept system that tries to demonstrate these ideas. Now, I know this is a lot of text, but it's actually just a few things. The system maintains a state that's a set of image indices, say maybe image indices 1 through 100, but generally not. It's some subset of all the images we've seen so far. It maintains a smalls tracker state or the 2D tracking data for just those images. So if the images in the state are images 1 through 50, and then images 75 through 100, you've got smalls tracker output for those 75 images. Then there's a variable state dimension filter for the images in there. And again, if you've got, say, 1 through 50 and 75 through 100, you've got 6 off-camera position estimates and 3-dimensional positions of the points you tracked for 75 images. And then the last thing are just the SIFT key points for the most recent image, which we're going to extract and try to use to see if we've come back to a place where we were before. Okay, so just a really brief example. Suppose we've been through the first 9 images in the sequence, images 0 through 8. At the end of that, our state will contain 9 images, 0 through 8. And in the this doesn't have to generally be true, but in the proof of concept system that I built, I divide the states or the state sequence into rollback images and non-rollback images. And the rollback images are basically just the states that, as we go on through time, we're going to consider as possible revisitation points. So, for example, if we're up to image 8, and for some reason we suspect that we're back close to the position where we were at the time of image 3, then we'll reload the state for image 3, and we'll try the smalls tracking and the VSDF estimation into image 8. Okay, and then if we decided for some reason that the estimate that was produced by those 5 images, 0 through 3 and 8, was better than the estimate we got by integrating all the way forward from 0 to 8, maybe we'll prune off that relatively poor estimate from 9 images, and we'll just take the 5 image estimate. Okay. And then you can continue to do this. If you continue to take every 3rd image as a rollback image, then you build a kind of tree over time that shows kind of the best way to estimate our current position using all the data we've seen so far and by kind of opportunistically rolling back. Okay. And then the question is when to roll back. So the process that I used, which is efficient, but, well, not too efficient, it could use some work, it's a proof of concept, is look at the estimated covariance we have for the current position, and look back at our rollback states, and kind of immediately throw away those rollback states where the camera covariance is larger. Our idea is to minimize the error in the camera position. So if we think the error is larger in some previous rollback state, it's probably pointless to roll back to that high error state. Then we do SIFT matching between the current image and all the surviving rollback states. If the number of SIFT matches is higher than some threshold, I think it was 300 in the example I'm going to show you, then the things where the number of SIFT matches is higher than the threshold survive. We then extend from the candidate state, meaning the possible rollback states, into the current image. And then once we've done that, we re-examine the covariances again. So for instance, if we've tracked from 3 to 8, we examine the covariance that results from that rollback against whatever our previous estimate was. And then I should say, we take, if we considered 0, 3, and 6 as rollbacks, we roll back to what image produces the smallest covariance. Okay, so I've got a nice example of this. What I did was I came into the CMU Field Robotics Center late one night at like 2 a.m. when nobody was around. It was after a poker game, but I was sober, and I took 940, the number will come up, it's 945 images, I think. And these are some of the images from that sequence. So the first one is kind of looking at one of the PC workstations. The second one is the door to a bridge between two buildings. Here's the Hyperion work area. And then this thing on the right is like an overhead door in the high bay. Okay. And then this is the floor plan of the high bay that I worked in. And what the sequence does is it does what I call the first forward pass. It's the first 213 images. We start there on the right by the computer workstation. We back up and we move forward to that door. We back up again and we go a little further in the high bay and we kind of move up to the Hyperion work area. We back up once more and we go out to the overhead door. And that's the first 213 images. And then in the subsequent 160 images or so, we do what I call the first backward pass. So we back up basically the whole way. And then there are 4 more passes, 2 more forward passes and 2 more backward passes that are similar to these, for a total of 945 images. And the question is, it's a relatively long motion. We see a small bit of the scene at any one time. Can we really accurately estimate our motion over that time? Now, before I show you the video, one caveat is that, like I said, generally this idea of rolling back can produce a kind of general tree of states. In this case, for clarity, and because my implementation is a relatively slow prototype implementation, what I did was I looked at the sequence and I said, well, we mapped the whole place in the first 213 images. So I'm not going to let it roll back in the first 213 images, but in the subsequent 900 and some images, I'm going to let it roll back only to states within the first 213. And I've kind of schematically showed it there as every third image being a rollback state, but in fact I used every 10th image for this example. Okay, and now the movie shows you the smalls tracking output on the bottom for the sequence. And then on the top you'll see its estimate of the 6-DoF camera motion and the 3-dimensional point positions viewed from above. So on the far right you'll see when it starts out, during the first 217 images it maps the whole place. With the camera positions and their covariances in red, and then its estimated 3-dimensional point positions in yellow, again, viewed from above. Now, during the other 5 passes, the 3 rollback passes and the 2 forward passes, what you'll see there is the same global map that it constructed during the first 217 in white and blue, and then just the current state in red and yellow. So, for example, here what's happening is we're up to image 301, but it decided it could roll back to 110. So what we have is a state that's the first 110 images plus image 301, and the red and the yellow are the camera positions and the point positions that we can derive from those. Okay, let me show you that. Okay. So it starts off, like I said, by this workstation, and it goes to this door going to the other tunnel. And you're seeing the 2D smalls output on the bottom and a top-down view of the 3-dimensional position on the top, or the 3-dimensional estimates. It's getting close to the end of the first pass now. It gets out to the high bay door. And then it starts this first backward pass where it kind of retraces its steps. And if you watch the top, occasionally it will decide it's close to some previous image. It rolls back and it produces an estimate with a better camera error than what it had. Okay, so that was the end of the first backward pass. We're on the second forward pass. And this process kind of continues. Error always kind of accumulates. The error is a little different on every pass. And if it thinks it can opportunistically reduce that error by rolling back, it does it. Now, like I said a little earlier in the talk, smalls actually can be still defeated by a really bland area or a really repetitive texture in the images. So, for example, coming up, you'll see that it will hit a kind of grid wall right here. And there's a big area where it can't really track anything accurately. So at that point, it's kind of defeated, and it throws up its hands, and it says, I have no idea where I am until it hits an image that it can roll back to. The overhead door is another one of those areas. In some of the images, basically all it's seeing is the overhead door, which is almost purely a one-dimensional texture. Okay, and that's the last image, 944. We've come back to the workstation, and because, it can roll back to image 0 or image 10, it pretty much knows exactly where it is, even though it's 940 images later. Okay, so let me just conclude. This entire system it was a lot of chunks, actually. When you think about the image-based estimation, the image and inertial estimation, the smalls tracker, the rolling back. It's a pretty large code base, and it's all done in C++ by hand, so none of it's really optimized. For a real system like a MAV or something like that, you'd want to run this in real time, so you'd want to have an optimized system. Like I mentioned earlier in the talk, the image and inertial online algorithm, which is a Kalman filter, probably should be replaced with a VSDF or sliding bundle adjustment type method that fixes its problems. With smalls, we have the inertial data. One way to specialize smalls that would really be helpful would be to incorporate the gyro data. Now, the accelerometer data is harder to incorporate because you need to estimate more things, but a gyro is actually a pretty simple instrument to incorporate. So with a little bit of pain, we could do that and get better smalls output. And then with this long-term system, I've done a lot of heuristic things for the rolling back process that should be fixed for scalability. Okay, and that's the end. I just want to say thanks, and then I'll give you the URL again for these online materials. And I'm happy to take any questions. Okay. I'm sorry?
How do you represent your rotations?
Oh, yeah, the question is, in bundle adjustment, how do I represent the rotations? And I've represented the rotations using Euler angles, which are kind of the minimal representation for a 3D rotation. They do have some technical problems. For instance, some rotations are represented by an entire space of equivalent Euler angles, which isn't ideal. For those types of applications, we probably want to switch to quaternions or something like that. Okay. All right, well, no.
Introduced your combination of inertial and camera together, that you didn't find it very effective against large loss of place. Did I hear correctly?
So the question was, is it correct that by adding inertial data into the estimation that we didn't really improve the robustness to, say, large motions or losing our position? Actually, it's almost exactly right. Really, the problem was on a finer level. And that was that even sometimes if we mistrack between individual frames, just one frame to the next, that's a killer for bundle adjustment or a Kalman filter image-only method. And we found that adding inertial data didn't really give us robustness to even that smaller problem. And certainly with our cheap sensors, the issue you address, which is if we lose our place over a longer span of images, or we're kidnapped where we don't know what position we might be at all, certainly with our cheap inertial sensors, we can't integrate over such a long interval to fix that problem. So that was, at Honeywell, we've been talking a little bit about, Honeywell's, they're world experts on inertial navigation, and so we're talking a little bit more about trying to use some more real hardcore inertial sensors to fix that.
What can you say about if you lose things all the time, move to a completely different position, of course.
Yeah.
It's quite useless, but more locally making very sharp movement. One would think that inertial corrections would be good exactly for that, even if the motion couldn't use it very well, still be okay. You could rely there locally on inertia and restricting the motion. So isn't that
Yeah, so the question is roughly, if you have an erratic motion, that type of quick short-term motion seems to be the type of motion that inertial sensors would actually be very good at. And that's true. The only advantage we lose in that case is that, we're not exploiting the images in that case to try to minimize the inertial motion. We do a split the joint estimation problem using image and inertial measurements into basically almost two separate estimates that are joined by an inertial integration, which is fine. But I'm happy to talk more about it. So. I haven't. The question is, have I experimented with subspace tracking? And I haven't done that. For 3D. No, I haven't done anything like that. So. Okay, well, thanks again.